On August 2, 1985, Delta Airlines Flight 191 was on approach to Dallas-Fort Worth in clear visual conditions. The crew could see the runway. The aircraft was on profile. Everything was normal. Then, in approximately 37 seconds, the aircraft went from a fully controlled approach to a catastrophic impact with the ground. 137 people died. The weather that killed them was not a hurricane, not a tornado, not a severe thunderstorm. It was a column of air approximately 1 mile wide falling from a cloud at speeds exceeding 40 knots. It had no radar return. It was invisible to every instrument on the aircraft. It was undetectable by the ground-based weather radar at Dallas-Fort Worth. When the aircraft entered it, the physics of what happened were so precisely lethal that the outcome was mathematically determined the moment the nose crossed the microburst boundary. The crew had approximately 37 seconds. They did everything right. It was not enough. Because the force they were fighting, a column of descending air that first accelerated the aircraft, then destroyed its lift, is a physical phenomenon whose behavior at the scale that kills aircraft was not fully understood when Delta 191 entered it. And here is what makes this story genuinely disturbing. Parts of it are still not fully understood today.
A microburst is a specific meteorological phenomenon, a concentrated downdraft of air that descends from a thunderstorm or convective cloud and strikes the surface, then spreads outward radially in all directions. The physics of why a microburst is so specifically lethal to aircraft on approach is a sequence of events so precisely timed that it appears almost designed to defeat the available response time. Phase 1. Headwind increase. As an aircraft approaches the outer edge of a microburst, it encounters the outflow spreading from the impact point of the downdraft. This outflow is a headwind relative to the aircraft's direction. A headwind increases airspeed. Increased airspeed increases lift. The aircraft performance improves. The crew, seeing increased airspeed, may reduce thrust, the natural response to maintaining approach speed. Phase 2. Downdraft. The aircraft enters the core of the microburst, the column of descending air. The downdraft pushes the aircraft toward the ground. The crew increases thrust and pitches up, the correct response. But here is the physics that makes the next phase fatal. Phase 3. Tailwind. As the aircraft exits the far side of the microburst, the outflow spreading away from the impact point becomes a tailwind. A tailwind reduces airspeed. Reduced airspeed reduces lift. The crew, already at high thrust from fighting the downdraft, is now experiencing simultaneous loss of airspeed and proximity to the ground. The aircraft has been first accelerated, then pushed down, then decelerated, in a sequence specifically calibrated by the physics of the phenomenon to exhaust the available energy margin at exactly the wrong moment. On Delta 191, that sequence took 37 seconds, insufficient time to rebuild energy before the ground.
The aviation industry's response to the microburst problem was one of the most intensive weather physics research programs in the history of aviation. Dr. Theodore Fujita, the meteorologist who developed the tornado classification scale still used today, analyzed the crash of Eastern Airlines Flight 66 at JFK in 1975, the crash of Pan Am Flight 759 in New Orleans in 1982, and the crash of Delta 191 in Dallas in 1985. His analysis established, for the first time, the precise three-phase headwind, downdraft, tailwind structure of the microburst encounter as a coherent meteorological event. Before Fujita's analysis, aviation investigators knew that wind shear had caused these accidents. After his analysis, they understood exactly what wind shear was doing at each phase of the encounter. This was the scientific foundation. The next problem was detection. A microburst is typically 1 to 4 kilometers wide and lasts approximately 5 to 15 minutes at full intensity. Its formation can be triggered by a process called virga, precipitation falling from a cloud that evaporates before reaching the ground, cooling the air it falls through, increasing its density, and causing it to descend with increasing velocity. The evaporation, and therefore the downdraft, can begin at altitudes where ground-based radar cannot detect precipitation. The downdraft is happening. The radar shows nothing. The aircraft enters the approach. The microburst forms beneath the cloud base in less than 5 minutes. The aircraft is on final approach when the microburst reaches maximum intensity. The timing is not coincidental. The physics of convective precipitation and approach corridor geometry create this encounter configuration with statistical regularity over hot, humid airports during summer afternoon thunderstorm activity. The problem was not just detecting microbursts, it was detecting them fast enough.
The technological response to the microburst problem produced two systems that are now standard at commercial airports worldwide. The first, Doppler weather radar. Traditional weather radar measures the return signal from precipitation. It shows where it is raining. Doppler radar measures the frequency shift of the return signal. It shows not just where rain is, but how fast the rain is moving, toward or away from the radar. When a microburst forms, the precipitation in the downdraft is moving toward the ground. The outflow spreading from the impact point is moving away from the center in multiple directions. Doppler radar sees this signature, the radial divergence pattern of the outflow, as a distinctive pattern on the display. The low-level wind shear alert system and the terminal Doppler weather radar, installed at major airports in the United States following the Delta 191 accident, can detect this pattern and issue automatic alerts to air traffic controllers within minutes of microburst formation. The second, airborne wind shear detection. Modern commercial aircraft are equipped with weather radar systems that also use Doppler processing, detecting the horizontal wind velocity changes in the airspace ahead of the aircraft. Predictive wind shear systems alert the crew 30 to 60 seconds before the aircraft would enter the hazardous region, sufficient time, in most circumstances, to execute a go-around and avoid the encounter entirely. These two systems, ground-based and airborne Doppler, have been credited with eliminating the type of fatal approach phase microburst encounter that killed 600 people between 1975 and 1985. In the United States, there has been no fatal commercial aviation microburst accident since the installation of these systems became universal in the mid-1990s. The technology works, with one significant limitation.
The limitation is one of scale. Doppler weather radar, ground-based and airborne, detects microbursts by reading their effect on precipitation. The precipitation has to be there for the radar to see it. But approximately 30% of microbursts, specifically in hot, dry environments like the desert southwest of the United States and in specific arid regions worldwide, are dry microbursts, virga precipitation that evaporates completely before reaching the ground. No precipitation, no radar return, no warning. The downdraft is fully formed. The outflow is spreading, the approach corridor is compromised, and the radar, both on the ground and in the aircraft, shows nothing. Dry microburst detection remains an active area of research. LiDAR systems, light detection and ranging, which can detect air movement directly without requiring precipitation, have been tested for airport-based wind shear detection and show significant promise. But LiDAR systems are expensive, require line-of-sight operation, have limited range in certain atmospheric conditions, and are not yet universally deployed at international airports. The NCAR, National Center for Atmospheric Research, and the FAA's Aviation Weather Center continue to model microburst formation at the convective scale, the scale at which a thunderstorm's internal dynamics determine whether a downdraft will form, how fast, over which corridor, and for how long. The models are good. They are not yet good enough to predict the specific microburst that will form in the next 5 minutes over a specific approach corridor. That prediction, the one that would provide complete warning for every microburst regardless of precipitation, requires understanding convective dynamics at the spatial scale of meters and the time scale of seconds, at the intersection of meteorology, fluid dynamics, and thermodynamics, where the physics of the air you breathe meets the physics of the atmosphere that weather systems build. It is an open problem. The technology has saved hundreds of lives by solving most of it. The remainder, the dry microburst, the sub-radar phenomenon, the 5-minute warning gap, is what atmospheric scientists are still working on. The aircraft keep landing, the storms keep forming, and the edge of what the radar cannot see is where physics research still needs to go. Follow for more about the atmospheric science hiding at the boundaries of what aviation technology can and cannot yet detect.